So welcome everybody. Today's presentation, as I mentioned, today we're going to talk about ThreadX package in Julia. And the talk is actually divided into two parts. So the first part, I'm going to talk about traditional multi-threading in Julia with these threads and the issues that you see there. And then I will jump into ThreadX and will show you how you can solve most of these issues. So first, a little bit, let's just start with a quick overview of programming languages in Julia. So in Compute Canada, users use many different languages. So on our clusters, C, C++, Fortran, scripting languages such as Python, R, and new parallel languages such as Julia and Chapel. So we teach all of these languages, including Julia. And so in WestGrid, we've been teaching Julia for about 2 years now. And we teach both a serial introductory Julia, and we have various courses in our summer schools, winter schools, etc., on parallel Julia. We also did a number of webinars on Julia, and you can access these on the same webpage where you can find these slides. So I also want to mention quickly that in 2 weeks, we're going to have a 3-day, well, actually it's February 14th, 16th, and 18th. So we have 3 sessions. Each session is going to be on a separate day, and it's going to be focused on parallel Julia programming. So there's going to be lots of hands-on exercises, and there we'll talk about various topics in parallel Julia, not just multi-threading, but also multiprocessing, shared and distributed data structures, etc. But today we're really focusing on multi-threading. So I'm going to show all examples on my laptop, and also I'm going to show you, I have a slide where I ran some benchmarks and tests on our Cedar cluster, and I will show you how to install packages there, etc. So I mentioned in the abstract that this is going to be a fairly introductory webinar, and I assume that not everybody knows the difference between threads and processes. So this is very basic, but I think I should probably explain this. So in Unix, a process is the smallest independent unit of computing. So think of a separate application, right? So for example, you're running a browser. Browser is going to be typically a process. You're running a I don't know, text editor is going to be a process. So a process typically has some memory space allocated to it. Also has register stacks, so short-term memory, and local memory. And also the pointer to the position in the code where, which is running right now, right? So it's an independent unit of processing in the sense that the operating system, Unix or Linux, tries to isolate different processes as much as possible, in the sense that typically a Unix process cannot really read the memory of another Unix process very easily. So a process can have multiple threads, right? And if you are running on a system that has multiple CPU cores, then in principle, each thread can run on its own CPU core. And that way you can actually utilize multiple cores at the same time. So you're going to run a parallel computation, a parallel process, right? A parallel process with multiple threads inside. And each thread is going to run on a separate CPU core. So your application, your program, your process is going to run faster. So if you have multiple threads inside the same process, all these threads are sharing the same virtual memory address space of that process, right? So that means that in order to exchange information, in order to talk to each other, threads will use a shared memory. So there's no messaging, they talk to each other via shared memory. If you talk about context switching, so context switching for multi-threading is very fast. So usually it takes, I don't know, milliseconds to maybe 10 milliseconds to launch a thread, right? So for a process, it is much longer. So it's tens or hundreds of milliseconds. So context switching between processes is much slower than between threads. So, but that's good for us. So if we have a system where we have multiple CPU cores, then we can actually launch multiple threads and switch between these threads. And in principle, if you have more threads than the number of CPU cores, then some threads will be taking turns running on the same CPU core, right? But that context switching is actually pretty fast. So you don't really lose much in performance, in terms of performance, if you have more threads than the number of CPU cores. But there are several caveats to this, so I'll mention this later on today. Are there any questions about threads versus processes at this point? So here on the slide, you see we have, I have 2 pictures. So that the picture on the left shows a single, a process with a single thread. So it's just a single thread, and there's some memory allocated to that process. Whereas the picture on the right shows a multi-threaded process. you have some shared memory heap, and then you have some local memory that is local to each thread, right? But all these different threads can talk to each other via shared memory. Okay, so in Julia, multiprocessing has been built into the language for the last 2 or 3 years, so since version 1.3, and it's part of the base threads library. So when you install Julia, base threads is already installed. You don't need to install it separately. And the way you use it is you simply call, you call either add threads macro or various functions from the threads library. So let me just start Julia locally on my machine. So I'm going to start for now serial Julia. So this is serial Julia running. And then what I'm going to do is I'm going to say threads and inquire about the number of threads, right? So this is using the not ThreadsX, not the main topic for today's webinar, but the built-in system. So I'm going to say threads and then number of threads, and it's going to show 1, right? So if I don't want to type every time a threads dot, what I need to do is I'm going to say using base and then threads, and then now every time I call this function, I don't need to preface it with threads dot. So now I want to switch. I'm going to use multiprocessing, so I'm going to switch to multiple threads. In Julia, the usual way to do this in modern Julia is by passing the flag to Julia at startup. So -t is going to launch multiple threads. And I'm going to use, because I have 8 cores on my laptop on the CPU, I'm going to quit Julia, and I'm going to restart it with 8 threads. So now if I say using base threads and inquire by the number of threads, it's going to say you have 8 threads available. Okay. If something is not clear, if I'm going too fast, feel free to pause me and ask questions. All right, so to speed up a loop, what you can do, well, just run a loop in parallel. You can simply have your loop. So here we have a loop. Let me just copy and paste this loop into my Julia session, right? So here we have a serial loop. So for I from 1 to 10, print iteration I on thread. Well, actually, I'm using thread ID here, but because I'm running serial loop, thread ID always returns 1, right? So I'm just running on thread number 1. But in fact, it's very easy to parallelize these with built-in multithreading. All you need to do is just put add threads macro before the loop. So this is the usual, those of you who are new to Julia programming, this is fairly common way of extending the capabilities of the language and extending the language in Julia is you can put a macro in front of a code block, and that will modify the code block. In this case, is going to make it parallel by multi-threading, right? So I'm going to run the same, do the same, but I'm going to say add threads, and then now it's running in parallel. So there are 10 iterations, and then you see that these iterations are broken roughly into how many groups. So we have 8 threads, but actually it looks like I'm actually using all 8 threads, right? So it's just divided these 10 iterations among the 8 threads. Okay. So now let's compute the sum of integer numbers from 1 to a million using multiple threads. So here we have the code, right? So when we run this code, the problem with this code is it's not thread safe. So when I paste this code and I run it, every time I run it, so here I reset total, and then every time I run it, I'm going to get a different result, right? So this code is not thread safe. So here we're using a global variable, well, global in the context of the for loop. So it's set outside the loop, and then we're simply running through all numbers from 1 to a million, and then we update that total variable. And as you can see, every time we run it, we get the different result. And so the problem here, this happens because all threads are updating the same variable, and they're doing this at the same time. So while one of the threads has just updated the variable, another one uses an older value of that variable to update the value, and so we have a conflict. So this code basically is not thread safe. That is what is called race condition, right? So multiple threads are trying to update the same variable at the same time. So unfortunately, with built-in base threads, built-in multi-threading in Julia, you don't have any reduction support. So I'm not sure why it wasn't programmed, but you have to do it by hand, right? So one way to do this is by using an atomic variable. An atomic variable is a variable that has a log, and whenever any thread is writing to an atomic variable, only that thread can update the variable. So all other threads have to pause and to wait for the lock to be removed in order to be able to write into this variable. So that means that most of the time, most threads will be waiting for a lock to be removed, right? So this code is supposed to be slower than a more optimized code, right? So here we have an atomic variable, and in order to update an atomic variable in Julia, you actually cannot do it directly. You cannot use just the equal sign. You have to use a function like atomic add to increment it by I, right? So here we're incrementing in parallel, and then we're printing the total. Right? So, but I already mentioned this code is probably slower than a more optimized code. So let's try to do some benchmarking. And I have a slide on benchmarking in Julia, so I show it in all my parallel Julia courses. So benchmarking in Julia is somewhat different from benchmarking in other languages. There are several caveats. So here, let's consider a very simple code. We're running so this is a serial code, and we're running a sum of going in numbers from 1 to a billion, right? So that's an integer billion. And then here we have a total set to 0, and then we update total with I. And then we're going to print the total, right? And then here we're using the another macro, add time macro, for timing. So this is good. Add time macro is built into the language, and it's good for timing things that take a long time. So, seconds or multiple seconds. And then when I run this on my laptop, these are the run times I get. So roughly, every time I run, I get 51 seconds or so. All right. So now, so here the problem is with the code on the left is that there are several problems here. One of the problems is that the add time actually includes the JIT compilation time, right? So it's not very large. It's certainly much smaller than 51 seconds. But add time, the first time you run it on, let's say, on a loop, it will actually compile that loop, and then it will it will run it. But time will include both compilation and the runtime. Another problem here is that total is a global variable to the loop, and using global variables is actually really discouraged in Julia. It's not very optimal, especially in a code that is not packaged into a function. So now let's have a more optimized version of this code. So here I actually define a function that is called quick of n, right? So n is going to be the upper limit of summation. I'm going to pass a billion to it eventually. And then here I define a variable total. So, but this variable is now local to the function, right? So when I first run the function is getting precompiled, and total becomes basically, it's not now a global variable, it's a local variable to the function. So, and then I time only the summation, right? So going from 1 to a billion, then I return total. And then when I run this function, it will also print the timing for in seconds for the loop only. So I run it the first time to precompile the function. Right now the function is precompiled, and then I run it like this. So I'm going to say print total and then pass an integer billion to it. And in the previous version of Julia, so now the latest version of Julia is 1.7.0. And in the previous version of Julia, if you were to do something like this, you'll actually get the runtime 0 seconds, exactly 0 seconds, and then you will get a correct result. Well, 0 seconds sounds really suspicious because before in serial, sorry, not in serial, before when we didn't have a function, it was taking 51 seconds. So, 0 microseconds sounds really suspicious. So let's try to increase the number and see if we get something non-zero. And with Julia 1.6, if you increase the number to something ridiculous, like in this case, 1,000 trillion, right, 10 to the 15, it still gives me 0 microsecond runtime, which just cannot possibly be true, and also gives the incorrect result. So the incorrect result, you can trace it back to the limited integer 64 precision, so that's not the problem. The problem is the 0 runtime. And the reason this happens, it turns out that Julia is actually too smart for this code. It knows that all it needs to do is just add up a bunch of integers from one number to another, and it will replace the summation with direct summation with a formula, right? So actually it doesn't compute the sum. I did this recently try this in the latest version 1.7, and in 1.7 actually seems to be doing direct summation. So Not sure why such a difference between 1.6 and 1.7. But the problem here is that when we do benchmarking, we really want to make sure that we're running actual computations, that we're not replacing this computation in the compiler by a formula. So what I'm going to do is I will force a computation. So I will have somewhat more complex computation. I'm going to show it in the next slide. And so I will enforce computation. Also, when we do benchmarking, it's very important to exclude compilation time, make use of optimization for type stability. So basically, at runtime, Julia needs to know all the types of all variables, and that will make it more faster, more efficient. So the way to solve this, both of this problem is we're going to package our code into a function and precompile it the first time we run it. And then we're going to time only the CPU intensive loops. And then for shorter runs, milliseconds or up to a few seconds, it's very common in the Julia community, instead of using add_time macro that is built into the language, to use the add_btime macro from the benchmark tools. So the beauty about add_btime macro is it will give you measurement in milliseconds or seconds, but it will run the code multiple times, right? And then it will take all those individual measurements and it will report back the shortest time, right? So presumably, if the CPU was busy, running some other applications, then the shortest time will actually be more accurate. And it will also, add_btime macro will also precompile the function, right? Which is great. All right, so the problem I'm usually using for teaching Julia and doing benchmarking in Julia is the slowly converging series. And what it is it's actually a really elegant mathematical problem. So it's well known that a traditional harmonic series, 1 over k, where k runs from 1 to infinity, diverges, right? So it turns out that if you omit terms that contain any digit or any string of digits in decimal notation, this harmonic series will converge. So for example, if we take all 1 over k's, but we only include keys that do not have digit 0, so we omit all terms that have a digit 0 in decimal notation, then it will actually converge to this number, 22.9 and so on. So this is actually the exact problem I'm going to be using today a lot for benchmarking. And then if you omit other digits or successive digits, it will converge to other numbers. And this convergence is actually very, very slow. So with no terms with a decimal 9 digit, in order to get 4 significant digits in the answer, you actually have to compute 10 to the 73 terms. And if you want to have more precision, it gets to a ridiculous number of terms. But this is actually good for us because I know that the number I get should be smaller than the exact number, right? And I'm actually doing real calculations. So in order to exclude digits from the denominator, you have to be able to check that you don't have, in this case, a digit 9 in our number, right, in our term. And one way to do this would be to check for substrings in a string. So it's actually really easy to do in Julia. If you have a string, you can simply say if digit 9 occurs in a string, then then do not include this term, right? So it turns out that this calculation is actually fairly slow, and you can replace this with an integer calculation. So thanks to Forcesharing from BBC, he actually showed me this code, and it turns out that if you do this in integer, the code is slightly longer, but it's 4 times faster than the code than checking for a substring. Right? So this is the code I'm going to be using for the rest of this webinar. So what I'm doing here, I'm passing two integer numbers. One is I'm going to pass number 9. So it's going to check if number 9 is present in the decimal notation in this number, right? So this is going to be the term in my summation, well, actually 1 over the term in my summation. And then it will return either true or false, depending on whether digit 9 is present or not. So let's actually do this once. I have all the timings in my slides, but let me just do it once. So I'm going to define, let's see if I can copy from this slide. Not sure if it will work or not. So let me paste this code. So now I'm running on 8 threads. Okay, I'm going to start with the serial code. No, actually, no, I didn't. Let me paste from my text editor. So pasting from a PDF sometimes doesn't work well. So here I define the digits in, and you can actually see if I run it, it will, so let's see 9 digit 9, and then let's see in 123, oops, digits in. is going to return false. If I add digit 9 here, it's going to return true. So it works. Now, let me go back to my slides and show you the serial code. So I'm going to do first benchmarking of the serial code. So I'm going to use not built-in add time macro, but I'm going to use the add btime macro from the benchmark tools package. And then this is my function, right? So it's a serial function. Here I have total, and then I simply go through all the numbers from 1 to a billion, and then I include 1 over I if 9 is not present in the denominator. Okay, so let me copy this code from the function slow and using the benchmark tools from my text editor. All right. And then what I'm going to do is I'm going to say total and then add btime slow. So here is, if you're new to Julia, again, this is syntax that is not kind of obvious, but what I'm doing here, so I'm calling the slow function, passing digit 9 to it, right? So here's my digit 9, and then the upper limit of summation, 1 to a billion. And then it's running, and it's actually, because I have btime here, so it's running multiple times. It will run maybe, I don't know, 5 times or something like that. And then it will do those individual measurements, and then it will give me the shortest run time, right? And that already excludes compilation time. So here I have 5.4 seconds, right? And this is done so that you will see throughout today's webinar. Okay, great. So it takes 5.4 seconds to run this code in serial. Okay, let's time now the parallel code. So the parallel code with the atomic variable. So remember, the atomic variable is a variable that only one thread can run to at the same time. And here I have 8 threads, and I'm not going to run this. I already ran this, so it takes a little bit longer because it turns out that this code is actually slower than the serial code. So when I run this code, again, using add btime macro, and I run the code in serial, well, running in serial, you just need to start Julia with 1 thread. So here, for example, I have all this code you see in the slide is packaged into the script atomitthreads.jl, along with the definition of the digits in function, right? So I also need the definition of this function. So all of this is packaged into a file atomitthreads.jl, and then to run it, I run it just from the command line. So I'm going to say Julia, pass the script name to it, and it runs, and it prints back the result and the timing, the shortest of all runs. And so here for serial code, I get also almost 6 seconds. So it's a little bit shorter. It's a little bit slower than the serial code, which is expected because now it's actually doing atomic variable and running function multiple times. But it's interesting that when I run it with 8 cores, so I have 8 physical cores on my machine, it turns out that it is a lot slower. So instead of 6 seconds, I get 38 seconds or so. And so the reason for this is because we're using an atomic variable, which was not really meant to be used for reduction, right? So atomic variables are primarily used for synchronization, but they have really bad performance. So you have 8 threads in this case trying to write into the same variable. Most of the time, most threads are not doing anything. They're just waiting for the lock to be released. So they're waiting to be able to write into the variable, right? So it's actually, this is something that is peculiar to my notebook, to my laptop. If I try to run this with 6 threads, it turns out it's actually 15 seconds or 16 seconds, right? So it's more than twice as fast compared to 8 threads. And this is, so what's happening here, why I see much better runtime with 6 threads than with 8 threads, is actually, I have a MacBook M1 with, M1 processor with 8 cores. But of these, 6 cores are high performance cores, and 2 cores are high efficiency cores. So the high efficiency cores are much slower, right? So in this case, when I'm trying to use all cores, both high performance and high efficiency cores, the high efficiency cores are much slower, and they're dragging the time down because they're so much slower to run, to update the atomic variable, and all other processes also have to wait for them, right? So that's why in this case, with this particular code, running with 6 threads actually produces better results, but it's still not good compared, it's still 3 times as slow compared to the serial code, right? So using atomic variables for reduction is not a good idea. All right, here's another Threadsafe implementation. So Threadsafe safety means that every time you run this code, it will produce exactly the same result. And here I have, what I'm doing here is instead of having, in the previous code, I had just a single variable total. Now I have an array. So let's say we have 8 threads, and then I have an array of eight double precision scalars, right? And then each thread will update its own scalar, right? So I'm only, so from thread ID given thread, I'm writing into the respective element of this array. So I will have 8 partial sums, and then I compute the total sum, and then I time this into operation, right? So when you do this, when you write in serial, again, in serial takes 5 point something seconds on my laptop. When I run this in parallel using 8 threads, it's actually 3.8 seconds, which is not great, right? So what is going on? So there's certainly a problem with this code. And the problem is not really, so those of you who are from computer science, you will probably know what the problem is. But the problem is really, it's called Forcesharing. So you can actually, there's a Wikipedia page on this, you can Google it. And it turns out that, cache lines in a processor are chunks of memory handled by the cache. And typically they are somewhere between 32 and 128 bytes. And it turns out that when you run multi-threaded code, at a time, only one thread can write to a cache line. So if you have another thread that is trying to write to the same cache line, it will have to wait its turn. So these cache lines will attach to a thread, and then will need to attach to another thread, and so on. So the problem arises when you have these compact arrays. So in this case, we have an array in the previous code. We have an array of 8 threads, so 8 elements, right? And they're close to each other in space. And it turns out that all of them happen to fall into the same cache line, right? So that's why it takes forever for individual threads to actually write into these variables. So one simple solution is not terribly elegant, but it works really well, is to space these elements by some factors. So if you use a factor of 8, this will assume a 60-byte cache line, right? So it will separate them, all those individual partial sums in memory. And then we can time this code, right? So here we are simply, instead of writing into thread ID element, we're writing into element thread ID times space, right? Separating this in space by using some gaps. And it turns out that this code is faster. So before we're getting a very small speed up with 8 threads, 3.8 seconds. Now, if I run it with 8 threads, I get 900 milliseconds, right? Which is pretty good. So this is almost, well, a factor of 7 speed up, which is not bad, considering that you have 8 threads and 2 of these are high efficiency. So not very, sorry. 2 of these are low efficiency cores, so not very high performing cores, right? All right. Here's another, so last example before going to ThreadX of a code that also is Threadsafe. And this code uses manual task parallelism. So here I'm computing exactly the same problem, but here I have multiple threads, and then I'm computing inside each thread, I'm computing the starting and the finish index of the subloop that the thread is supposed to compute, right? So, and actually we can print this. So if you have a loop from 1 to a billion, then, and you have 8 threads, then the first thread will be responsible for processing elements from 1 to 125 million, and so on. And you have more or less equal division of labor between the threads. And then I'm also using this space factor here. And then I get very similar timing. So here, the timing is also roughly 900 milliseconds, which is a factor of 7 or so speed up compared to the serial code. All right, so this works, but you have to be aware of issues, right? So you have to remember that add threads, built-in add threads, does not include reduction. And also you can run into problems, as I showed you. So you can run into performance issues, into this Forcesharing effect, and so on. So a lot of manual things that you have to do if you want to compute the, do reduction with multi-threaded parallelism in Julia. So ThreadX actually solves all these problems. So ThreadX is an alternative implementation of multi-threading in Julia. And the way they do this is actually not, the syntax is very different from the add threads macro that we saw with the built-in multi-threading. What they do is they take a number of functions, built-in functions in a Julia language, and they parallelize these functions. So these are called base functions, are basically the functions that are built into the language. And so you already saw base. Remember when we're loading the threads library, I was saying using base.threads. So whenever you start Julia, base is everything inside base is already in the namespace of your shell or your script. And yeah, so everything that all these functions that are inside the base library is already accessible to your Julius session. So now let's load using ThreadsX. So here I'm going to say using ThreadsX. And now everything inside of ThreadsX is available to me, but I have to use these prepended with ThreadsX dot notation, right? So I type ThreadsX dot, and then I hit tab twice, and it shows me about 20 or so functions. So these all functions that are present in the base Julia library. These functions also have a parallel equivalent provided by the ThreadsX package. So let's look something up. So let's do MapReduce and look up the manual page. So it says no documentation found, right? So by the way, you look up manual page, those of you who don't know, you type, so from the Julia session, interactive shell, you type question mark, and then you type the name of, well, whatever you want to get documentation on, and it says no documentation found, right? There are two methods for generic function MapReduce inside of ThreadX. So there are two different ways you can use it, but there's no documentation found. So I found that in ThreadX, actually, documentation is not complete, but the good thing is that functionally, all of these functions are exactly the same as their equivalent in the base library, right? So if you want to get help on this, all you need to do is just type question mark reduce, right? So this will give you help on the MapReduce in the base library. And then if I scroll up, you will see that what it does. So MapReduce, you supply a function to it, you supply an operation to it, and then you supply an iterator or a generator or a collection, basically a collection of items. And then it will simply apply the function to each element or each item in the collection. And then it will take all these partial results of, take all these function results, and then we'll apply a reduction operation on them, right? Reduce them to a single number. So let me show you an example. If I go to my slides, and then so here, what we're doing is, so here I'm using the base MapReduce, right? Not ThreadX MapReduce, but the base serial MapReduce. So what we have here is a range of numbers from 1 to 10. And then to each number, we're applying a square function. So this is a lambda function in Julia. Simply replace the original number by its square. And then take all the squares and apply the summation. So sum up all the squares of integers from 1 to 10. And when I run this, we get the result 385, right? So if I want to just sum the numbers, what I can do is I can simply modify the lambda function, and it simply gives us the familiar number. So 55 is the sum of integers from 1 to 10. All right. So there is another way you can use MapReduce, and I'm not 100% sure how this was programmed. So I'm relatively new to Julia myself. But another syntax that works is you can say MapReduce. Again, this is a serial version of MapReduce from the base library, base Julia language. And here you supply the mathematical operation, you supply the collection, in this case, a range of numbers. And then, so here there's no function, but the function is actually given by the second line. So you're going to say do I. So I runs from 1 to 10. And then replace the argument, so similar to a lambda function, replace the argument by the square of the number, right? So functionally, this is exactly the same as the previous example. Run through all integers from 1 to 10, compute the square of each integer, and then sum all of them up. So let me copy and paste this. And it gives exactly the same result as before. Okay. All right. So let's go back to our slow series code and parallelize it. So here we have the MapReduce. So I replaced the for loop with the MapReduce do syntax, right? So here we have the loop where I runs from 1 to n, and then if digit name doesn't occur in the denominator, then include 1 over I. Otherwise, simply add 0. Right? So this is what we'll be adding to the total sum, right? So these are the results from each function operation, and then with here we have the reduction operation plus, so we are summing all these results. and then return the total, right? So when I run this, it returns again the correct answer. And when I run this, I do timings. I have a serial timing, so the familiar timing 5.2 seconds, 5.3 seconds in serial. And then when I run it using 8 threads on my laptop, I get 900 milliseconds. So this is much better speed up than many of the examples you saw earlier with built-in multithreading, right? So here we're not running into the force sharing effect issues and into other issues. So the code is really fast, and all we needed to do is just replace the standard for loop with this expression, right? And that's it. So really easy to parallelize. Now, you can even simplify this code further. This is not related to MapReduce. It's just the more complex notation for an if-else loop in, statement in Julia. Instead of doing this using multiple lines, you can actually do it in a single line, right? So this is the shorthand if-else statement notation. So if this is true, then this is the result. If this is false, then 1 over I is the result. If this is false, then 0 is the result, right? And then total is going to be the result of summation for all these numbers. And then if we run it again in serial, 5.2 seconds. If we run it in parallel using E threads, we get 914 milliseconds. So very good speed up. And of course, if in this code, if you reduce ThreadX.MapReduce with just MapReduce, that will give you a serial code that will not run faster if you run it with multiple threads. Okay. Any questions so far? Okay. Let's continue. So so far we looked at the MapReduce function, right? Several different syntaxes for the MapReduce function, but of course there are many other functions. I'm going to show you just a few today because, well, we don't have a lot of time, and I just want to focus on the important ones in my opinion. So another function that is really useful is the sum function. So if we let me bring up help on the serial sum function. So what this function does is you supply a function, you supply an iterator or collection or generator, basically a range of numbers, could be a range of numbers. And then what it does, it will apply the function f to each of the elements in this collection, and then it will sum up the result. So functionally, this is very similar to the MapReduce function, right? Just different syntax. All right. And also, oh yeah, this is not, it's probably not even in the help. So the sum function will also, so if you supply, let's say an array, let's say 1, 2, 3, to the sum function, what this will do, it will simply sum up all the numbers in this array, right? The expected behavior. So here, let's use a generator. So a Julia generator is similar to, I guess, Python iterators. So basically, a generator is a fast way in Julia to produce a range of numbers without using a lot of memory, right? So very efficient, memory efficient way of iterating through a sequence. And the syntax is actually similar to what is called the least comprehension or array comprehension in Python, right? So here we simply have an object where we say I for I goes from 1 to 10. And what this does, so if you actually run this, it will, the expression in round brackets, it will tell you that this is a generator, right? Actually, it doesn't compute it. It simply tells you that it's a generator. But you can use this generator, right? So you can convert it to an array, for example. So you can do something like this. This is going to be an array of 10 elements. And then you can also pass these to a sum function, right? So here's a one-liner that replaces our previous code. So it replaces all the previous examples. So here where, again, I'm loading the benchmark tools in order to be able to use a bit-time macro. And then here I have this compact else if statement that says, if this is, if the not statement, not present statement is true, then include 1 over I, otherwise include 0. So this is a generator where we have a range of numbers from 1 to a billion, right? And this generator will produce a billion elements, right? It produces a billion elements, whether they're 0 or non-zero. And then you simply sum them up. So this is the serial code. This is using the base sum function. And then if you time it, it takes 5 seconds, produces the right result. And it's really easy to parallelize. To parallelize this code using ThreadX, all you need to do is, well, of course, you need to load the ThreadX library, and you simply change the sum to ThreadX.sum. And then you get the timing. So now you went from 5 seconds to 900 milliseconds, which is a fantastic speed up. There's a question: is it possible to use ThreadX with data frames? I have not thought about it. I have not seen any discussions of using ThreadX with data frames. I'm sure it is possible. I'm just not sure. So I have not used data frames myself in Julia. So I can't really answer the question, but I'm sure it is possible with a little bit of programming. But basically, I don't know the answer, so I will need to look into this. I just have not used data frames in Julia myself. But most likely, yes. All right. So alternative syntaxes. So here's something that is very similar to the last example on the previous page, except that here we, instead of having a billion elements in our generator, we have a few elements because we only include elements where the condition, this condition, so the not present condition is met, right? So do not include zeros, only include non-zero terms, right? And this actually a little bit faster than the previous example because now we have fewer terms in the generator. We exclude all those zeros. And now it runs in 888 milliseconds and still prints the right result. So here's yet another syntax. I can do this by defining a numerical function. So remember, when I brought up the manual page on the sum function, I said that what it does is it takes a collection, applies a function to each element in the collection, and then sums the results. Well, let's just use that syntax. So here we have a numerical function, and this numerical function simply returns either 1 over I or 0, depending on whether digit 9 is present or not present in the denominator. And then it simply applies this numerical function to every number in this range, right? So it's super easy to write this code. This is the entire parallel code plus the definition, obviously, of the numerical term and the digits in functions. And it takes 890 milliseconds, so really fast. And you can use the same syntax for the map reduce. So already brought up manual page on the map reduce before. And here we're using the same numerical function to each element in this collection, and then take the output of all these functions and reduce them to a single number using the summation operation. Again, runs really fast, 912 milliseconds. All right. So a few other functions I'm going to use this. I'm not going to go through all the functions. I think that map reduce, sum are the most interesting ones. And then I'm going to, when I talk about Julius sets in a few minutes, another really interesting function is the map function, which applies a function to each element in the collection without doing reduction. But a couple of other examples. So if you actually, there are other things in ThreadX. So if I type ThreadX.tab twice, then you see that there are various other things like maximum or minimum or sorting operation. So let's look into the sorting operation. So here I initialize an array of single precision floating point numbers with 100 million elements. And so here I'm just printing, showing you can print the the entire array, or you can print the first 10 elements, the last 10 elements, and so on. So here the point is I'm applying the in-place sorting function to this single precision array with 100 million elements. And in serial, it takes 1.4 seconds. So if you try to do it in parallel using the in-place sort, exclamation mark means in-place sorting, from the ThreadX library, it takes roughly just under 600 milliseconds, which is not a fantastic speed up. So it's a 2.3 or something like that speed up. But that just reflects the fact that sorting is intrinsically hard to parallelize because it's a communication heavy problem, right? So do not expect 100% parallel efficiency when you try to do sorting. So in this case, using 8 threads, we get a speed of 2.3 or something like that. So, so it's very difficult to get a much better speed up than this when you use multiple threads. Okay, so here's an example of looking for a maximum. So looking for a maximum. Minimum is much, of course, computationally less intensive than sorting of all elements. So here we have a billion elements. And of course, when you initialize an array like that with a billion elements, make sure that you have enough physical memory. Otherwise, you'll run into other issues. And so this takes roughly 4 gigabytes in memory. And then we are doing looking for maximum in serial, so that takes 288 milliseconds. And then when I'm doing this in parallel using ThreadX, that it just takes 32 milliseconds, which is a factor of even slightly better than a factor of 8 speed up, right? Which is fantastic. So simple operations like looking for a maximum minimum can parallelize very efficiently. So now the last big example I'm going to show you is also an example that I use a lot when I teach Julia, and it's a mathematical problem called the Julius set. So there's no relation to Julia language. What it is basically similar to Mandelbrot fractals. And what it is you have a complex plane, right? So on a two-dimensional complex plane, on the horizontal axis, you have a real value of a complex number, and here you have on the vertical axis the imaginary number of imaginary portion of the complex number. And then if you pick any point on this complex plane and start applying a function f of z, transformation f of z iteratively to it, so it takes a complex number, returns in the complex number, it turns out that you can get some interesting results. So the traditional form of this iterative function is z squared plus a constant, where a constant is just a complex number. And so it turns out that if you do this iteratively, some functions, some of these iterations will run to infinity, so they will be unstable, and some iterations will actually be stable. So the idea of these is to plot the stability for each point, right? So here we take a region -1 to 1, both for real numbers and for imaginary numbers on the complex two-dimensional complex plane, and then for each pixel, for each point on in this region, we run this function iteratively, and then we count the number of iterations at which point it diverges. So what is divergence? Well, basically, if it runs to infinity, then very quickly this function will pass some threshold, and we can set the threshold to anything we want. So I just set it to 4, right? So basically, there's a radius of 4 somewhere just outside this plot, and I record the iteration number at which my iterations for each point pass this threshold. So if my iterations are stable, they will never pass this threshold. So I need to limit iterations at some large number. I'll just use 255. And then if the points are unstable, then my iteration number is going to be much smaller, right? So here, basically, everything that is in has low values is unstable. Everything that has high values is in red is very stable, right? And then I just plot this as as a two-dimensional region. So you can try this with so the code I have in the next slide. You can try this with different values of the complex constant. So some interesting values I plotted here. If you try to run this code with these different values, you will see very different looking fractals. So here's the code. The code is really very simple. And all I'm doing here is loading it's a serial code for now. So I'm using the benchmark tools package and the plots package to actually plot the picture. So here I define the pixel function, which that does the iteration. So it takes a complex number from that plane, and then iteratively applies a function to it. So this is our constant, and here I'm just using a zoom out factor so I can actually feed these fractals into the plot. And then I run up to 255 iterations. So if my point is stable, it will return 255. If it's unstable, it will return something smaller than that, right? And then what I'm doing here is I define 2 arrays, and you can actually write this function. You can write this code without 2 arrays, just with a single array. And the reason I'm using 2 arrays, I will explain very shortly. So here I use the first array is an array of points, right? So an array of points where I use a 2000 by 2000 grid, right? And then I define a 2000 by 2000 grid of complex numbers in single precision. And then for each of these points, I also want to compute the stability. So stability is going to be a single precision integer. And then what I'm doing is, first of all, I'm defining all the points, right? So the reason of this, the point of this calculation is just to fit everything into the -1 to 1 rectangle. Okay? And then I will simply take each point, and then for each point, I'm going to compute the stability, right? So the stability is just the output of the iteration number from the pixel function. And then I'm going to take this two-dimensional 2000 by 2000 array stability, and then I'm going to plot it into a file. Okay, so here's the entire code. And then if I run it, Let me actually run it and see how long it takes. So I'm going to say, oops, I'm going to exit, and I'm going to go into the Julia set library. I'm going to say Julia, and then Julia set serial 1, just run it. So it will give me the timing, and the timing for the actual calculation comes from B time. So it means it will actually run it several times and report the shortest time. So let's just see. It will take maybe 5-10 seconds for the number to come up, and then it will also spend some time plotting. But I'm only timing the calculation of applying the pixel function. So here we go, 1.2 seconds, and then it's plotting to PNG. So that will take maybe extra 5 or 10 seconds. And here I'm going to show you the plot. Oops. And the plot went to different. So here's the plot that I just created. All right. But what we're interested in is timing. So 1.2 seconds, right? So now, if I want to parallelize this with built-in base threads, what I need to do is, of course, I need to, so I'm modifying the code. I'm just showing the difference between the code on the previous slide and the new parallel code. So I need to include the base threads library, right? Of course. And then I need to take my loop and change put add threads macro. So that's built-in multi-threading using the base .threads library. Putting the add threads macro in front of the loop to make it parallel. But here one caveat is that you cannot really do it with a nested loop. So here we have a nested loop, right? And add threads doesn't work with nested loops. So basically I have to break it into two loops and then parallelize the outer loop. But that should be fairly efficient because my outer loop well, it runs from 1 to 2000. So there are a lot of iterations. And then when I run it on each threads, I actually get 249 milliseconds, which is, the serial time was 1.1, 1.2. So not fantastic speed up. So speed up by a factor of 4.5, maybe 5, but certainly not 8. And so it's kind of slowish. And you could say that maybe the problem is in row major versus column major. So which iterations I use for parallelizing, whether I use rows or columns as the outer loop. So actually doing the faster one here. So that's not the problem here. So likely the problem is the Forcesharing effect. So the fact that you're writing into this array stability that, and also reading from this array. Well, actually reading from this array may be not a problem, but writing into an array is a problem. So when you're writing into elements that are sitting very close to each other in memory. And of course, fixing this with spacing is going to be more difficult and less efficient if you try to do, just a simple space variable. So you have to do something a little bit smarter. So the point here is that even though you can parallelize it with multi-threading, it's not very efficient. And to make it more efficient, it's actually quite a lot of work. Okay, so how do we parallelize with ThreadX? So the problem is that so far, everything I showed you in ThreadX was doing reduction, and we want to process an array without reduction, right? So what I want to do is take our array of points and then make it converted into an array of a stability factor, right? So basically, for each point, for each original point, we want to have the maximum iteration number, but we don't want to do any reduction. And so it turns out that there's a function for that in the base library that was parallelized with ThreadX. The function is called map. So let's bring a manual page and map. What it does, I'll go back to Julia, and then the manual page and map. What it does, it transforms a collection by applying a function f to each element, right? So this is very similar to MapReduce, except that you don't do the actual reduction, right? You just apply the same function to each element in the collection. All right, so you can actually use it in several different ways. So this way, what we're doing here is we're applying this function, so doubling each number to each element in the array, right? So when you run this, you actually, instead of 1, 2, 3, you have 2, 4, and 6. So this is slightly more complex. So there is a plus operation here. It's not a reduction operation. What's happening here is we take two arrays and then we add them up. And of course, these two arrays have different lengths. So what will happen is it will only take the first 3 elements of the second array. So it will report 11, 22, and 33. And then these guys are not going to be utilized, right? So this is not a reduction operation, just summing two arrays of different lengths. All right, and so here's a change I make to my serial code. So I simply replace the nested loop where I go through all points and computing the stability factor I simply replace that with a mapping operation, right? So I apply the pixel function to every point on the complex plane, right? So replace this loop with this map function, right? And the map function will simply go through all, how many, 2,000 squared points, and will apply the function to each point. And then when I time this, I get slightly better results from the previous serial code. So the previous serial code, I saw 1.1 and 1.2 seconds. Now it's 917 milliseconds, which is better. So that means that map is map. So the serial map in the base library is very efficient, much better to use it than to use built-in loops. So as expected, but it's also really easy to parallelize it. So to parallelize it, all you need to do is, of course, you want to load the ThreadX library, and then you simply change map to ThreadX map, which is the parallel version of the mapping of the map function without reduction, right? And then when you run it with each threads, it's actually you get a much better number. So you get 171 milliseconds. All right. So my last slide before summary, we are running out of time. Running in a cluster, you can run Julia. We have Julia installed on our clusters in Compute Canada. So I ran tests yesterday on the Cedar cluster, but it's the same on Niagara, Beluga, and Graham and other systems. So the latest version we have multiple versions of Julia available. So if you log into the cluster and type module available Julia, it will show you all the versions available. So the latest one I'm using here is 1.7.0. And by default, when you install packages, all of them will go into your .julia folder in your home directory, but it's actually really easy to install them elsewhere. So the way you do this is from Julia, you have to use these lines basically to override the default depot path, and then you type the closing square bracket to go into the package installation mode, and then you install any packages, and all these packages will actually go, instead of .julia folder in your home directory, it will go into, for example, Scratch folder, whatever you specify here. And then at runtime, when you load the Julia, so packages are installed, you load the Julia module, and you need to set up two variables, so the depot path and the load path. And so make sure you do it correctly. So the point here, don't copy and paste from the PDF. So double check this, maybe go to online documentation, but this should work. And this lets you install packages not into, let's say, slower home file system, but into any other file system. And of course, you can install packages not just not before running your job. You can also do it as part of your job as well if you want. So here I'm showing two scripts. One is for running serial code. The other one is for running Julia. So the very last example I showed you, so the multi-threaded version of map function using a certain number of threads. So here I'm submitting basically a single MPI task, multiple CPU cores. So using I tried 16 cores and asking for memory maximum. I mean, it takes only a few seconds to run this, but I just specified 10 minutes maximum runtime. And when I run this, it will run. So if I specify 16 here, it will launch 16. A single process with 16 cores. And then here's the timings I got yesterday on Cedar. So for serial code, it was 2.5 seconds. And then for a parallel code, I got a speed up on 16 cores. I got a speed up roughly by a factor of 12 or 13 or something like that, which is not bad at all, right? So really easy to run it in parallel using ThreadX on a cluster as well. So this is my summary page, and basically all I want to say, ThreadX is really fantastic. Use it. It solves many problems, and most likely, so I saw some discussions that people say that ThreadX will likely to be incorporated into the main language in the not too distant future. So if you want to see the list of supported functions, use ThreadX. So load, say using threads X, load the library into your session, and then say ThreadX, and then dot tap, and that will give you the list of functions supported. And then to bring up page, sometimes there's no built-in help on the function, so you can simply go to a documentation for a similar function in the base library and basically use it in the same way, but just replace it with the parallel version. And once again, a plug for the upcoming, so in 2 weeks, we're going to have the Parallel Julia National Training Workshop. Is going to be three 3-hour sessions, February 14th, 16th, and 18th. And there we're going to have lots of hands-on exercises, and not just multi-threading, but multiprocessing and shared arrays and distributed arrays as well.